Well, I'm very pleased to be seeing you again for this Module 2 on informal proportional reasoning. Module 1 was about oral and written arithmetic. Module 2 is about going beyond arithmetic and looking at quantitative reasoning and trying to identify the origin of informal proportional reasoning and when adults calculate in the informal economy, and trying to find the same origins in children's reasoning when they are taught about numbers in school. Now, why did we want to go beyond arithmetic? Our studies of street mathematics provoked the reaction that, okay, these children can't do arithmetic, but can they do mathematics, really? Well, arithmetic is the visible phase of mathematics, and that's why we could observe what kinds of productions the children offer to us in oral and written arithmetic. But reasoning is the invisible phase of mathematics. We don't see reasoning. We have to infer reasoning from what people do or what people say or what people write. So what we wanted to find was a form of reasoning that would be recognized by mathematics teachers as important, and then see whether we could observe that form of reasoning outside school. We chose to study proportional reasoning for several different reasons. First, proportional reasoning was recognized in psychology as a sign of formal operations. And in Piaget's and Inhelder's theory, formal operation is the most advanced form of reasoning attained by people. And formal operation is hypothesized to enable any kind of learning in mathematics. The second reason is that schools have great difficulty in teaching children about proportions, and it is a kind of reasoning that is pervasive and required in many problem-solving situations in mathematics. Now, we know that many situations in everyday life require proportional reasoning, and the challenge for us in research was to identify a situation in which people with no or little formal schooling would be required to use proportional reasoning. Proportions were taught in Brazil at that time when students were in 6th grade. So we wanted to identify people who had no schooling or schooling up to about 5th or 6th grade, but had to use proportional reasoning in their work life. Enlarging a geometrical figure is a typical proportions task used in schools, and many children and adolescents seem to have trouble in solving the enlargement of rectangles appropriately. So this is actually a real-life task for construction foremen who often have to look at blueprints and from the blueprint know what's the real size of the wall in the construction or the real size of a door opening or a window gap. Construction foremen in Brazil often have little or no schooling, and in our research we interviewed a few construction foremen who had no schooling at all. So this created the possibility of studying proportional reasoning developed outside school informally. Now, in order to design a task that would provoke the construction foreman to explain to us how they reasoned, we had to choose to present them with a scale drawing that didn't tell what the scale is. So at the time in Brazil, there were 3 scales that were used quite often. One, what they called 1 to 100, 1 to 1,000, and 1 to 50. Now 1 to 100 means that 1 centimeter on the blueprint represents 100 centimeters in reality, which is then 1 meter. Now, because only these few scales were commonly used in Brazil, what we decided to do was choose a scale that is not used in practice and present the foreman with a scale drawing in which they would have the drawing and we would indicate the size of a particular wall next to the drawing. So the construction foreman had to measure the drawing, look at the value indicated next to it, and from this pair of values, infer the ratio used in the blueprint. Now, in this particular example, the measure on the drawing was 5 centimeters, and we indicated that the wall was going to be 2 meters long. I want to share with you a solution offered by a foreman who was completely illiterate. And the way he described his educational background to me was, I don't even know how to draw my name. Now, he started by saying, on paper it is 5 centimeters. The wall is to be 2 meters. And then he said, now, one thing I have to explain to you. This is not a scale that we usually work with. And I agreed. I said, that's right. And he laughed and said, this one we will have to divide. I think you did this one on purpose. And then he engages in the solution using his measurement instrument and talking to me at the same time. So he says 1 meter is worth 2.5 centimeters. So the 2.5 centimeters he's now showing me in his ruler. 2 meters, 5 centimeters. 3 meters, 7.5 centimeters. But there's 5 millimeters more. So he's thinking that he had measured the target wall in the problem was 8 centimeters. So he says, but there's 5 millimeters more. If I have 2.5 of this one, and he shows me 2.5 centimeters on his ruler, worth 1 meter, this one divided by 5, then it's 20 centimeters, then you add, it is 3 meters and 20, and the it here refers to the wall. And then he smiles and looks at me and says, it's all done by reasoning. Clearly, it was all done by reasoning. This was an unfamiliar scale drawing, and he couldn't have known the solution. But let's listen to his solution and present it in a schema. So what he says is 1 meter is 2.5 centimeters. 2 meters, 5 centimeters. 3 meters, 7.5 centimeters. So he is constructing pairs of values. And then he does the division he says we have to do. So you divide 2.5 by 5 to have a half centimeter, and you divide 1 meter by 5 to have 20 centimeters, and then he adds 3 meters and 20. Now, if we try to understand the informal proportional reasoning, there are two salient features of this foreman's reasoning. And of course, his particular example is actually one example of several other observations like that. One thing that sticks out is really salient is the use of one-to-many correspondences. As he explains his reasoning, he establishes correspondences between what's on the scale drawing and what is the real-life wall. And it occurred to us at the time that the correspondence schema could be the origin for informal multiplicative reasoning. The second aspect of his solution that is quite salient is what Gerard Vergnaud called scalar calculations. And the calculations are always within each of the measures. So when he divides the size in the blueprint by 2, he divides the size of the wall by 2. When he multiplies it by 2, he multiplies the other measure also by 2. So these parallel scalar calculations keep the ratio between the two measures constant. My good friend Gerard Vergnaud, who wrote extensively on multiplicative reasoning and whose work was really fundamental to help me understand the foreman's reasoning, explained that scalar calculations are an early form of multiplicative reasoning, and functional reasoning, which we want to make sure children learn in school, is a later development. Now, the study was foreman was really interesting and allowed us to describe these two features of the informal proportional reasoning. But could it be that this really is a source for proportional reasoning across many situations? So what we tried to do was to find another situation where we would come across people who had little or no schooling and would still be required to use proportional reasoning. And we found this study situation by working with fishermen. And it really was very hard work. We had to go to the beach every day to carry out this study. I'm sure you would find that very hard work too. Anyway, we worked with fishermen in the northeast of Brazil, where they salt and dry the fish that they catch, and they often process this fish that's called whitebait, so that the fish is sold far from the coast. And they are aware of the fact that when they process the fish in this way, there is a loss of weight. We investigated if they understood that the relationship between the fresh food and the processed food is proportional. Now you can see from this photograph what hard work it was. We had to go to the beach and present fishermen with these problems. Now, in order to elicit verbal explanations, we had learned from other studies that we had to present them with tasks that had some novelty. And the way to introduce this novelty was to talk about shrimp and fish in the south of Brazil, where we could then talk about ratios that they wouldn't be familiar with. but they would accept to reason about these ratios. Our aim in these investigations was to see whether we could identify the same two features of proportional reasoning that we had observed with the foreman constructions. We could observe these also in the fisherman's reasoning. The use of correspondences between the two measures, which in the case of fishermen would be the unprocessed and the processed seafood, and the scalar computations. And according to Gerard Vergnaud's theory, we should observe exclusively scalar computations. Now here's an example of a problem and a solution. So we said to the fisherman, there is a kind of shrimp in the south of Brazil that gives 3 kilos of shelled shrimp for every 18 kilos you catch. If a customer wants 2 kilos of shelled shrimp, how much do you have to catch? Now this is an unusual problem in 2 ways. First, the aim of the fishermen is usually to catch as much as they want, and the loss in processing is something that comes afterwards. So this fisherman had to reason about the loss in processing and target catching a certain amount. So that's a really novel problem. The second novelty is that this ratio is completely unusual. And it's so unusual that some of the fishermen would say, well, this shrimp is too small, it's not worth catching. But still, they agreed to reason about it. Now, here's an example of one fisherman's solution. And I chose this example because, again, it was a completely illiterate fisherman. And this is how he reasoned about the problem. So he starts out by repeating the data in the problem, and then he says 1.5 kilos, meaning processed shrimp, shelled shrimp, would be 9, meaning fresh shrimp. And then he actually explains his reasoning. He says it has to be 9 because half of 18 is 9 and half of 3 is 1.5. So he has now carried out a scalar calculation and applied it to both quantities. Then he proceeds, and half kilo of shelled shrimp is 3 kilos fresh shrimp. Then it'd be 9 plus 3, it's 12. And he concludes that 12 kilos that I fish would give you the 2 kilos that you want. It was really quite hard to follow the reasoning of the fisherman on the spot, but I have produced a diagram that helps us think about how the reasoning works. It is quite clear that the two features of informal proportional reasoning that we observed with the foreman, we are observing again with the fisherman. It is quite clear that he is establishing correspondences between the shelled shrimp and the unshelled shrimp, and it's also clear that all his calculations are scalar. So this gave us confidence that we had actually identified something interesting about the origin of informal proportional reasoning. The next point in my career does not involve work in street mathematics, but in fact it involves investigating children's informal multiplicative reasoning in England. Peter Bryant and I decided to investigate the origin of children's multiplicative reasoning as distinct from additive reasoning. We thought that children use different actions, schemas, when they do addition and subtraction, and when they do multiplication and division in action. So let's reflect on the concept of action schemas. The concept comes from Piaget's work, and it's a very simple but very powerful concept. It is the idea that an action schema is an organized action that can be applied to many objects and many situations. So I present in this slide two situations that are quite different. The objects are different, the aims of the situations are different, but the schema of action is the same. If I were to ask a child, in each of these 4 houses live 3 dogs, how many dogs live on this road? The child could set representations of the dogs, let's say little tokens in correspondence to the houses, and solve this problem, which would be typically a multiplication problem in school. In the second example, the question is, there are 18 balloons. Each child that comes to the party is going to get 2 balloons. How many children can we invite? And the schema of action is the same. To set one child or one representation of a child in correspondence to the representation of balloons. So it's again a one-to-many correspondence schema to solve problems about very different objects and with a different aim, because now this problem would be solved in school by a division. So in synthesis, if the schema of one-to-many correspondence that we observed being used by illiterate or adults with very little schooling in the informal economy, if that is the origin of multiplicative reasoning, at what age, how soon can we observe this schema being used by school children? Can we observe it before the children are taught about multiplication and division in school? So the schema can be used in a variety of situations, and we found that it can be used by children. So I want to give you some video examples of how children solve problems using these schema of one-to-many correspondence. This child is trying to solve the problem. In each house in the street live 3 dogs. How many dogs live in the street? And you can watch how the child solved the problem. You can point if it helps you. That was absolutely brilliant! 12 dogs live in this house. And how did you figure out? I saw you were counting in a very clever way.
I did 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
What's really interesting in observing this child's solution is that he actually illustrates how difficult it is to use the schema, because the child has to keep track of 3 quantities at the same time. The child has to keep track of the correspondence between houses and dogs and of the increase in the total number of dogs. So he actually starts to make a mistake, catches himself, and illustrates very well the difficulty of using the schema. This is a 5-year-old child. I want to show you an example of another 5-year-old child now solving the second problem, which was a division problem. Because sometimes it's hard, isn't it?
together for you so you don't lose it.
We can invite 9.
Now, I hope you noticed that as the child manipulated the balloons, the child was actually counting children. When he takes the last pair of balloons, he tells me I can invite 9. So he is establishing the correspondence between children and balloons in his head. He's counting pairs of balloons as if they represent children. It is interesting to know that more than 60% of 6-year-olds can solve a variety of problems that would be solved later on by multiplication and division when they are given objects. But of course, they haven't been taught multiplication and division yet at that age. They solve the problems using objects and creating the schema of action of one-to-many correspondence. We talk about this situation as the children are forming reasoning systems that include their actions as part of their thinking. This is, in fact, a very Piagetian idea that the origin of quantitative reasoning is in the schemas of actions. But they do not know how to multiply and divide. So this brings us to the end of the research about the origins of informal proportional reasoning, and I want to finish with some conclusions and education implications. Mathematical reasoning in school is not outside school is not restricted to arithmetic. It involves reasoning about relations between quantities. Preschool children, like the adults in the informal economy, can use a variety of action schemas to reason about situations. But the action schemas used for addition and subtraction, or what Vergnaud called additive reasoning, and used for multiplication and division situations, or what he called multiplicative reasoning, are different. Action schemas for additive reasoning are joining, separating, comparing in one-to-many correspondence. They relate to part-whole reasoning. One-to-many correspondence is the multiplicative reasoning that allows children to reason about ratio and solve problems that would be solved by multiplication and division operation in schools. The educational implications of these studies I find particularly exciting, because what these studies suggest is that children can be encouraged to reason about situations before they start to learn the arithmetic appropriate for those situations in school. So they can start to reason about ratios without having to talk about ratios by using the action schema of one-to-many correspondence. And again, we come back to Freudenthal's basic idea that children can be taught to mathematize situations by reasoning about them without having to use the arithmetic operations that they will be learning in school. And the final implication is that the use of manipulatives by schools would have to be radically different from what it is most often are used for currently. Most often, people think of manipulatives of ways of representing numbers. But in fact, In these examples, children are using the manipulatives to represent relations between quantities, such as a fixed ratio between quantities. I want to give you some of the references to this work, and I want to leave you with the main themes that we are going to think about in Module 3. Modules 1 and 2 were about informal mathematics. Module 3 is going to be about understanding school mathematics and the distinction between quantitative reasoning and arithmetic, and how to form different kinds of reasoning systems, going beyond action schemas and learning to use the tools for thinking that mathematics offers us. Thank you for being with me in Module 2, and you can now proceed to Module 3.